Reality is not what it seems. The universe is governed by hidden mechanisms, so bizarre they challenge our very logic. We will explore 50 of these profound cosmic secrets, from the spooky connections between particles to the mysterious force ripping space itself apart. By the end, you will see the cosmos through the eyes of a cosmologist, understanding the fundamental puzzles that define our existence. Why does time only move forward? And what is the true nature of the vacuum we call empty space? What single cosmic mystery makes you question everything you think you know? Einstein's so-called spooky action at a distance is not just a curiosity. It is a fundamental feature of our universe, a hidden thread stitching reality together. Imagine two particles created in the same event, forever linked in a cosmic dance. Now separate them by billions of light years. The moment you measure a property of one, like its spin, the other particle instantly assumes the corresponding state. This connection happens faster than light, seemingly violating the cosmic speed limit. Einstein was deeply troubled by this, arguing it suggested quantum mechanics was incomplete. He believed no information could travel instantaneously, that there must be some hidden variables at play, yet decades of meticulous experiments have proven him wrong. The spooky action is real. This forces us to confront a startling possibility. The particles are not communicating. They are not sending signals. They are, in a very real sense, two parts of a single, non-local entity. The space between them is an illusion. Our classical intuition, built on a world of separate objects and clear locations, shatters against this quantum truth. This mechanism of entanglement might be woven into the very fabric of space-time, a foundational property of existence itself. How can reality be so deeply interconnected? This profound mystery pulls us toward an even stranger cosmic secret, one that questions the very flow of time. This invisible scaffolding, dark matter, exerts a gravitational pull so immense it dictates the very architecture of the cosmos. Think of a galaxy like a spinning carnival ride. The stars on the outer edge, according to the laws of gravity we understand, should be flung out into the void. They are moving far too quickly for the visible matter alone to hold them in orbit, yet they remain held fast by an unseen hand. This was the revolutionary discovery made by astronomer Vera Rubin. By meticulously mapping the rotation of galaxies, she found that stars at the periphery move at the same astonishing speed as those near the center. The only explanation was a massive, invisible halo of matter surrounding each galaxy, its gravity keeping everything from flying apart. We now call this shadowy substance dark matter. It is not merely a few hidden clouds of dust. It makes up roughly 27% of the entire universe, a dominant but completely invisible presence. It does not interact with light in any way. It does not glow, it does not cast a shadow, it does not block our view. We only know it is there because we can feel its gravitational grip on everything we can see. For decades, scientists have been hunting for the particle responsible. They have built detectors deep underground, shielded from cosmic rays, hoping to catch the faintest whisper of a collision with a dark matter particle. They have looked for signals from space and created beams in powerful particle colliders. The candidates have names like WIMP, which stands for Weakly Interacting Massive Particles, or ACTIONS, hypothetical particles so light they could be produced in the hearts of stars. Yet, so far, the true identity of dark matter remains one of cosmology's most profound secrets. It is the hidden framework upon which galaxies are built, the silent architect of the cosmic web. If it were not for this mysterious substance, our universe would look entirely different, and we would not be here to ponder it. What other invisible architects are silently shaping our reality, completely undetected by our most powerful instruments, while dark matter pulls the cosmos together? An even more dominant and baffling force is doing the exact opposite. Dark energy is actively pushing the universe apart at an ever-increasing rate. This is not a gentle, steady expansion, but a runaway acceleration that defies our most basic understanding of gravity. Imagine you toss a ball into the air, and instead of slowing down and falling back, it shoots away from you faster and faster, vanishing into the sky. That is precisely what our universe is doing on a cosmic scale. The discovery of this phenomenon was so shocking it earned the Nobel Prize in Physics in 2011. Astronomers made this breakthrough by studying the light from distant stellar explosions called Type I, a supernova. These supernovae act as cosmic mile markers, their brightness revealing how far away they are. To everyone's astonishment, the most distant ones were much fainter than expected. The only explanation was that the space between us and them had stretched more than anyone predicted. The expansion of the universe was not slowing down due to gravity, it was speeding up. This accelerating push is attributed to a mysterious repulsive force we call dark energy. It makes up a staggering 68% of all the energy and matter in the cosmos. Think of it as a kind of negative pressure woven into the fabric of empty space itself, a constant energy inherent to the vacuum. On the grandest scales, this anti-gravity force overwhelms the pull of both dark matter and all visible matter, driving galaxies away from each other at a frightening pace. The leading theoretical explanation is Einstein's cosmological constant, a term he originally inserted into his equations to keep the universe static and later called his greatest blunder. Perhaps it was not a mistake after all, but a prediction of this vast, hidden energy. Other ideas suggest evolving fields of energy, known as quintessence, that change over time. But the true nature of dark energy remains one of the greatest unsolved problems in physics. This hidden mechanism dictates the ultimate fate of everything. If the acceleration continues unchecked, it points toward a cold, lonely end for the cosmos, where galaxies are torn so far apart that the sky goes black and the universe dies in a state of profound isolation, a fate known as the Big Freeze. Or, in a more dramatic scenario called the Big Rip, the expansion could become so violent that it tears apart galaxies, then solar systems, then planets, and finally the very atoms that constitute reality itself. What could possibly be the source of this immense, invisible force that controls the destiny of the entire cosmos? This relentless push leads us directly to another profound puzzle, one that questions the very substance of reality. The very emptiness of space is not empty at all. According to our best theories of the quantum world, the vacuum is a chaotic sea of energy, a frothing foam where virtual particles flicker in and out of existence in a constant, furious dance. This quantum jitter should fill every cubic centimeter of the cosmos with a staggering amount of energy, a repulsive force so immense that it should have ripped the universe apart in the first instant of its existence. Yet when we look out at the cosmos, we see something entirely different. The actual energy of empty space, what we call the cosmological constant, is incredibly small, almost zero. The discrepancy between the theoretical prediction and the observed reality is not just a small error. It is the most shocking failure of a prediction in the entire history of science, a number that is off by a factor of 1 followed by 120 zeros. This is the cosmological constant problem, a yawning chasm in our understanding that pits the rules of the very small against the rules of the very large. How can the vacuum energy be so potent in theory and yet so feeble in reality? This is not just a calculation error, it is a fundamental crisis. It means that either our theory of quantum fields is profoundly wrong when applied to the cosmos, or our theory of gravity is incomplete, or there is a miraculous cancellation happening that we do not understand. Some physicists like Steven Weinberg have suggested a startling possibility, the Anthropic Principle. The idea is that the cosmological constant must be small for life to exist. In a multiverse of countless universes, each with different physical constants, we simply happen to live in one of the rare, finely tuned pockets where the vacuum energy is negligible, allowing galaxies and stars to form. Others look to theories like supersymmetry, which posits a hidden symmetry between particles and could, in principle, cancel out the vacuum energy to a large degree. Yet supersymmetry has not shown up in our particle colliders, leaving the problem wide open. This fine-tuning is so precise it is like balancing a pencil on its tip for billions of years. It suggests we are missing a crucial piece of physics, a hidden mechanism that perfectly reconciles the quantum frenzy with the cosmic calm. What deeper law of nature could possibly enforce this impossible balance, connecting the infinitesimal to the infinite? Gravity is the force we know best, the pull that keeps our feet on the ground and our planet in orbit. Yet in the subatomic world, it is almost non-existent, weaker than all other forces by a factor so immense it defies common sense. This is the hierarchy problem. To grasp the scale, picture the electromagnetic force that holds atoms together. Now imagine gravity is 10 trillion times weaker. This is not a small difference. It is as if the other fundamental forces are powerful, roaring waterfalls, while gravity is the faintest whisper of mist. The energy scale where gravity finally becomes strong, known as the Planck scale, is a quadrillion times larger than the electroweak scale, where other particle interactions occur. This vast desert of energy between them implies something is terribly wrong with our picture. The problem centers on the Higgs field, the invisible energy field that gives particles their mass. The mass of the Higgs particle itself is incredibly sensitive to quantum fluctuations from every other particle in the universe. These fluctuations should naturally drive the Higgs mass up to the colossal Planck scale, making it impossibly heavy. For the Higgs to have the relatively light mass we observe, an almost perfect cancellation must occur. The positive and negative contributions from other particles must balance with a precision of 1 part in a quadrillion. It is like balancing a mountain on the head of a pin and having it stay there for billions of years for no apparent reason. This absurd fine-tuning suggests we are missing a fundamental mechanism. One elegant proposal is supersymmetry. This theory posits that every known particle has a hidden superpartner. An electron would have a selectron, a quark would have a squark. These partner particles would produce their own quantum fluctuations, perfectly cancelling out the destabilizing effects of their standard partners and neatly solving the hierarchy problem. The universe would possess a beautiful hidden symmetry. Yet, despite decades of searching, the Large Hadron Collider has found no evidence for these superpartners. Another startling possibility is that gravity only seems weak because it is leaking. Our universe could be a 3-dimensional membrane floating within a higher dimensional space. While other forces are confined to our membrane, gravity could spread out into these extra, unseen dimensions. Its strength would be diluted from our perspective, explaining its apparent feebleness. If true, this could mean that gravity is actually as strong as the other forces, but we only experience a faint shadow of its true power. Each of these ideas points toward a reality far stranger than we perceive, with hidden symmetries or unseen dimensions orchestrating the forces we take for granted. The hierarchy problem is a silent alarm. a profound clue that our current model of the universe is incomplete. What other scaling mysteries, what other hidden relationships between the immense and the infinitesimal are waiting to be uncovered in the quantum realm? This brief but violent growth spurt solved two of cosmology's deepest puzzles in one stroke. The first is the horizon problem. Look at the cosmic microwave background, the ancient light from the early universe. No matter which direction we point our telescopes, this afterglow has the same temperature to an astonishing degree of precision. This should be impossible. Those regions of space were too far apart to have ever been in contact, with no time for heat to flow between them and equalize. It is as if you walked into a room and found 100 cups of coffee, all at the exact same temperature, without anyone ever stirring them. The second puzzle is the flatness problem. The geometry of our observable universe is incredibly flat, meaning parallel lines never meet, and the angles of a triangle always add up to 180 degrees. For this to be true after 14 billion years of expansion, the density of the early universe had to be fine-tuned to 1 part in a million trillion. The initial conditions required for our universe seem impossibly special. Cosmic inflation erases these problems. By stretching a tiny, homogeneous patch of space to a size larger than our entire observable universe in less than a blink of an eye, it ensured that everything we see today came from a region that was once in causal contact. Everything was once stirred in the same small pot. This immense stretching also flattened the cosmos, just as blowing up a balloon makes its surface appear flatter and flatter. The theory pioneered by Alan Guth proposes that a mysterious energy field, dubbed the Inflaton field, dominated the universe for that fleeting instant. This field possessed a peculiar kind of negative pressure, acting like a kind of anti-gravity that pushed space itself apart at an exponential rate. Then, just as suddenly as it began, the Inflaton field decayed. Its immense potential energy converted into a hot soup of particles, reheating the universe and setting the stage for the Big Bang we traditionally study. But the most profound legacy of inflation is not the problems it solved, but the seeds it planted. The quantum jitters of the Inflaton field itself, those tiny fluctuations inherent to the quantum world, were stretched to astronomical sizes. These minute variations in density became the gravitational seeds for all future structure. Every galaxy, every star, every planet we see today grew from those microscopic ripples, imprinted onto the fabric of space during that first fleeting moment. We see the echo of these seeds in the faint temperature variations of the cosmic microwave background, a baby picture of the universe. Yet for all its success, the Inflaton field itself remains a ghost. We have inferred its existence and its general behavior from the cosmic structures we observe, but we have no idea what it actually is. Was it a fundamental scalar field, a cousin to the Higgs? Did it connect to a theory of quantum gravity? What triggered its decay, ending the inflationary epoch and giving birth to the familiar universe? The answers are locked away in that first unimaginable fraction of a second. This act of cosmic genesis, which crafted the blueprint for everything, is a mechanism whose fundamental nature we have yet to grasp. How did those first quantum whispers in the void dictate the grand architecture of the cosmos we inhabit today? The universe's first and most critical decision was to choose matter over antimatter. Our very existence hinges on this one fundamental imbalance. According to all known laws of physics, the Big Bang should have produced a perfectly symmetrical creation, an equal amount of matter and its mirror image, antimatter. For every quark born, an antiquark should have emerged. These opposing partners would have immediately sought each other out, annihilating in a flash of pure energy. The entire cosmic experiment should have ended right there, leaving behind a vast, empty, and luminous void. there should be no stars, no planets, and certainly no one to wonder why they are here. Yet here we are, something tipped the scales. A tiny 1 in a billion preference for matter over antimatter allowed a residual surplus to survive the Great Annihilation. That minuscule excess is everything we see, everything we are. This necessary breaking of the perfect symmetry is known as charge parity violation, or CP violation for short. It means the laws of physics themselves treat particles and their antiparticles slightly differently. We have observed this subtle bias in particle accelerators. When certain exotic particles like kaons or B-mesons decay, they do so in a way that produces matter very slightly more often than antimatter, but there is a colossal problem. The amount of CP violation we have measured in the lab is far, far too small to account for the overwhelming dominance of matter in our universe. It is like finding a single drop of water and trying to explain the existence of all the oceans. So where did the rest of the imbalance come from? Cosmologists are hunting for a hidden mechanism that acted in the universe's first moments. One compelling idea is leptogenesis. This theory suggests that extremely heavy, hypothetical neutrinos decayed in the early cosmos, and in their decay, they violated CP symmetry on a grand scale, producing a surplus of ordinary matter. Another proposal is electroweak baryogenesis, which imagines a dramatic phase transition as the universe cooled, similar to water freezing into ice. Bubbles of the new phase expanded, and their walls acted as factories, generating the matter-antimatter asymmetry as they moved. These are not just abstract ideas, they are testable. The properties of neutrinos we observe today could be the faint echo of those heavy ancestral particles from leptogenesis. And if electroweak baryogenesis is correct, it should have left a specific signature in the Higgs field, a ripple we might one day detect. The search for this answer is a search for our own origin story. Why did the universe break its own perfect symmetry to allow for something as fragile and complex as life? The answer is written in the behavior of the most elusive particles, pulling us deeper into the quantum shadows. Our very atoms possess a secret stability we take for granted. The proton, one of the fundamental building blocks of every nucleus, seems utterly permanent. Yet many of our most ambitious theories of physics insist this cannot be the whole story. Grand unified theories which attempt to merge the electromagnetic, weak, and strong nuclear forces into a single, elegant framework make a startling prediction. They suggest that the proton, the very heart of matter, should not be stable forever. It should eventually, very rarely, fall apart. These theories calculate a proton lifetime so vast it is almost incomprehensible, exceeding 10,000 trillion years. To test this, scientists have built some of the most patient experiments in history. Deep inside mines in Japan, the Super Kamiok and detector holds 50,000 tons of ultra-pure water, surrounded by incredibly sensitive light sensors. It is constantly watching, waiting for the telltale flash of light that would signal a single proton decaying within its vast volume. After decades of observation, the result is profound silence. Not a single confirmed proton decay has ever been seen. This non-discovery is one of the most important results in modern physics. The stubborn stability of the proton places severe constraints on how the universe could have unified its forces in the first moments after the Big Bang. It tells us that if a grand unified theory is correct, it must include some hidden mechanism, perhaps a new symmetry or a conservation law we have not yet discovered, that protects the proton and ensures the longevity of matter. This is not a failure, but a brilliant clue. The proton's refusal to decay is a cosmic signpost pointing toward a deeper layer of physical law. It suggests that the stability of the atoms that make us up is not an accident, but the consequence of a hidden principle woven into reality's fabric. What unseen shield protects the integrity of matter itself, and what does this reveal about the universe's ultimate blueprint? The vacuum of space is not the silent void it appears to be. According to the precise mathematics of quantum field theory, every single point in the cosmos should be a maelstrom of activity, virtual particle pairs borrowing energy from the vacuum itself, flicker into existence for the briefest of moments before annihilating each other. This quantum jitter should fill the vacuum with an immense, seething energy, a repulsive force of staggering proportions. When physicists calculate this predicted vacuum energy density, they arrive at a number so colossal it defies comprehension. Yet, when we measure the actual energy of empty space through the accelerating expansion of the universe, what we call dark energy, we find a value that is almost zero. The two numbers are not just slightly different, they are separated by a factor of 1 followed by 120 zeros. This is not a small error. It is the single greatest discrepancy between theory and observation in the entire history of science, a crisis known as the Vacuum Catastrophe. Think of it this way. The theoretical prediction suggests the vacuum energy should be so powerful that it would have blown the infant universe apart in a fraction of a second, preventing any star or galaxy from ever forming. The observed reality is a cosmos that expanded gently enough for structure to emerge over billions of years. How can the vacuum be so full of potential in our equations, and yet so serene in our telescopes? This catastrophic mismatch points to a fundamental flaw in our understanding. Either our theory of quantum fields is profoundly incomplete when applied to the cosmos as a whole, or our theory of gravity, Einstein's general relativity, is missing a crucial piece. Some physicists search for a hidden symmetry in nature, a principle that would force all these wildly fluctuating quantum contributions to perfectly cancel out, leaving behind the near-zero vacuum energy we observe. Others propose that our very concept of the vacuum is wrong, perhaps in a true theory of quantum gravity, where spacetime itself is quantized. The idea of a smooth, continuous vacuum energy simply does not apply. The vacuum catastrophe is a stark reminder that the emptiness surrounding us is the deepest of all cosmic mysteries. It is a silent tension between the rules of the infinitesimally small and the behavior of the infinitely large, a hidden mechanism whose resolution may require us to rewrite the textbooks of physics itself. What profound secret lies within this nothingness waiting to be uncovered? Our three-dimensional reality, with all its depth and volume, might be nothing more than a magnificent illusion. The holographic principle proposes that our universe is a projection from a two-dimensional surface, a cosmic hologram where every event, every particle, and every force is encoded on a distant boundary. This radical idea emerged from the fiery logic of black holes. When something falls into a black hole, it seems to vanish, taking its information with it. But this violates a core tenet of quantum mechanics, which states that information can never be truly destroyed. This is the black hole information paradox. To resolve it, physicists Gerard T. Hooft and Leonard Susskind realized that all the information describing what fell into the black hole could be entirely encoded on its two-dimensional event horizon, the point of no return. The three-dimensional interior, the black hole itself, is just a projection of that data. The universe, in this view, operates like a hologram on your credit card. The flat, two-dimensional surface contains all the information needed to generate a perfect three-dimensional image. In the cosmic version, the entire universe we perceive could be a holographic projection from a vast, two-dimensional shell at the edge of space. This is not just a metaphor. The mathematics of string theory and quantum gravity strongly supports this possibility. It suggests that the fundamental building blocks of reality are not particles or strings within space, but bits of information, like the ones and zeros on a computer chip, painted onto the fabric of spacetime's ultimate boundary. If this is true, then our experience of depth, of moving through a three-dimensional world, is a powerful and convincing illusion. The true laws of physics are written on a flat, cosmic screen, and we are the shadows dancing within. How can a flat surface contain the information for a whole universe? The encoding works through an incredible density of information. Every tiny plank-sized area on the boundary can hold a single bit of information. The sheer number of these microscopic pixels on a surface as large as the universe is enough to describe everything within it. This principle bridges the worlds of information theory and geometry, suggesting that space, time, and gravity themselves emerge from a more fundamental layer of quantum data. We are living inside a computation, a cosmic projection whose source code remains hidden on the edge of everything we know. Stephen Hawking's great insight was that black holes are not truly black. They glow with a faint heat, slowly leaking radiation into the void. This Hawking radiation arises from the violent quantum fluctuations at the very edge of the black hole, its event horizon. A pair of virtual particles pops into existence. Normally, they would annihilate each other in an instant. But if one particle falls across the horizon, its partner can escape, carrying away a tiny bit of the black hole's energy. Over eons, this process causes the black hole to shrink and ultimately evaporate, vanishing completely. And here lies the heart of the paradox. The Hawking radiation that escapes appears to be completely random, a featureless thermal static. It carries no imprint, no hidden code, no memory of the magnificent stars, planets, or atoms that fell in. When the black hole is gone, all that information seems to have been erased from the universe. This violates a sacred principle of quantum mechanics. Information, the specific quantum states that define every particle, must be preserved. It can be scrambled, hidden, or transformed, but it can never be truly destroyed. The universe, according to quantum law, must keep perfect records. So, where does the information go when the black hole dies? This question forces a direct confrontation between Einstein's general relativity, which says matter and its information are irretrievably lost behind the horizon, and quantum mechanics, which insists that cannot happen. One universe cannot contain both truths. For decades, physicists have proposed startling solutions. One terrifying idea is the firewall. The event horizon might not be a smooth, empty space as relativity predicts. Instead, it could be a wall of blazing energy, a cosmic shredder that instantly incinerates anything crossing it, preserving information by burning it into the outgoing radiation. But this contradicts Einstein's principle of equivalence, the very foundation of general relativity, which assures an astronaut would feel nothing special as they crossed the horizon. Another, more elegant resolution is holography, which suggests the information of everything that falls in is not lost inside, but is instead perfectly encoded on the two-dimensional surface of the event horizon. The black hole's interior is a three-dimensional projection of that data, and the Hawking radiation is not random at all. It contains subtle correlations with that surface data, a complex quantum encryption that we are only beginning to decipher. Recent work in string theory and the study of quantum entanglement points toward this kind of preservation. The information might escape, not in the individual particles of radiation, but in the intricate quantum links between them, a story written in the relationships of countless photons. Yet the precise mechanism by which a black hole performs this ultimate act of quantum data recovery remains one of the greatest hidden mysteries. Unlocking it would not just tell us the fate of information. It would reveal the very language with which space-time and quantum mechanics speak to one another, the secret code that unifies all of physics. What other cosmic ciphers are waiting to be read in the dark hearts of these gravitational giants? Magnetic fields weave through the cosmos like invisible threads, guiding the birth of stars and channeling cosmic rays across unimaginable distances. We find them not only within galaxies but also in the vast, nearly empty spaces between them, a discovery that poses a profound puzzle. If these fields were generated solely by stars or swirling galactic gas, the great cosmic void should be completely empty of magnetism. Their presence there suggests a far more ancient origin, a hidden mechanism that magnetized the universe in its fiery infancy. One compelling possibility is that the seeds of these fields were sown during cosmic inflation. As space expanded exponentially, quantum fluctuations in a primordial electromagnetic field could have been stretched to astronomical sizes, imprinting a faint magnetic fingerprint across the entire cosmos. Another theory points to the violent phase transitions of the early universe. As the cosmos cooled, it may have undergone shifts similar to water freezing into ice, and these cosmic rearrangements could have generated colossal electric currents, birthing the first magnetic fields in the turbulent plasma of creation. Once these primordial seeds existed, a process known as a dynamo could have taken over. Imagine the turbulent motion of ionized gas within a young galaxy, a swirling, conductive fluid. This motion can act like a natural generator, twisting and amplifying a weak magnetic field, stretching it and strengthening it over millions of years until it becomes the powerful force we observe today. The challenge is determining which of these stories is true. Are we seeing the amplified echo of a quantum whisper from the dawn of time, or did magnetism arise later from the sheer chaos of cosmic weather? The answer is written in the strength and structure of the fields we detect in the deepest voids, a fossil record of a hidden force that helped shape the universe we call home. What other invisible currents flow through the emptiness, silently directing the evolution of the cosmos from the shadows? A strange alignment cuts across the sky, a cosmic scar that should not exist. We call it the axis of evil, a name that reflects just how deeply it disturbs our understanding of the universe. This axis is not a physical structure but a pattern of unexpected alignments found in the oldest light we can see, the cosmic microwave background. The hot and cold spots in this ancient afterglow are not scattered randomly as our standard models predict. Instead, they show a peculiar preference, lining up along a specific direction in space, as if the entire cosmos were spinning around a hidden pivot point. This discovery strikes at the heart of a foundational belief in cosmology, the cosmological principle. This principle states that the universe, on its largest scales, should look the same in every direction and be smooth and uniform no matter where you are. It is the idea that we do not occupy a special place, that the cosmos is isotropic and homogeneous. The axis of evil suggests we might be wrong. One possibility is that this is a colossal fluke, a statistical anomaly that just happens to appear in our particular slice of the observable universe. Perhaps it is even a subtle systematic error, a ghost in our measurement machines that we have not yet managed to exorcise. But if it is real, the implications are staggering. It could mean the universe is not the same in all directions. It might have a preferred axis, a fundamental lopsidedness written into its fabric at the moment of creation. Some theorists look to cosmic topology, the idea that the shape of space itself is folded in a complex way. Imagine our universe is not infinite and flat, but finite and shaped like a hall of mirrors with its dimensions wrapping around on themselves. In such a space, light could travel on preferred paths, creating the illusion of large-scale alignments like the axis of evil. Others consider even more radical ideas, that this pattern is a fossil from a time before the Big Bang, an imprint from a previous cosmic cycle or a collision with another universe. It might be a sign that our cosmic inflation epoch was not perfectly uniform, that the Inflaton field itself had a directional preference, stretching space more in one direction than another, and leaving behind this primordial whisper of asymmetry. This hidden axis forces us to confront a profound question. Are we, in fact, at the center of a cosmic pattern? The alignment seems to point eerily toward our solar system. While this almost certainly does not mean we are literally at the center of the universe, it could indicate that our local motion through space is creating a strange kind of lensing effect, a shadow that we misinterpret as a fundamental feature. Or it could be a genuine clue that the universe possesses a hidden architecture, a directional grain like wood, that influences everything from the formation of galaxies to the very flow of time. What other large-scale anomalies are woven into the cosmos, waiting to reveal that our universe is far stranger and far less random than we ever dared to believe? The universe's first 3 minutes should have left a clear chemical fingerprint, a precise recipe of light elements forged in the primordial fire. For the most part, the predictions are spectacularly accurate. The observed amounts of hydrogen and helium in the oldest stars and gas clouds match the Big Bang's calculations almost perfectly, but there is one glaring, stubborn exception. Lithium, the third element on the periodic table, is about 3 times less abundant in the ancient universe than our theories say it should be. This is not a small accounting error. It is a fundamental mismatch between our model of cosmic genesis and the actual fossils we dig up from the cosmos' infancy. Something is wrong with our recipe for the first nuclei. The discrepancy could mean we are missing a key nuclear reaction pathway from that frantic first few minutes, a process that somehow destroyed primordial lithium as it was forming. Or it could point to something far more exotic. Hypothetical particles, such as those predicted by supersymmetry, might have been present in the seething early plasma. These particles could have altered the delicate balance of nuclear reactions, changing the rates at which lithium was created and destroyed before the universe had even cooled enough for atoms to form. This would connect the fate of a tangible element to the hidden world of particle physics. Yet another possibility is that we are blaming the Big Bang for a crime committed later. Perhaps the primordial lithium was produced in the expected amounts, but then early generations of stars consumed it. These ancient stars, burning with a different chemistry, might have efficiently shredded lithium in their fiery cores, leaving behind the deficit we observe today. The lithium problem is a cosmic cold case. It forces us to question whether the flaw lies in the first instance of creation, in the turbulent life and death of the first stars, or in the shadowy influence of particles we have yet to discover. Why would the universe so meticulously follow the recipe for hydrogen and helium, yet so conspicuously deviate when it comes to lithium? This elemental mystery reminds us that even our most successful cosmic stories still have missing pages, waiting to be filled in by the light of a distant star. Even the most precisely plotted journeys can be knocked off course by forces we never anticipated. The twin Pioneer probes 10 and 11 were humanity's first emissaries to the outer planets and beyond, racing toward the stars with incredible momentum. Yet as they sailed past the orbit of Pluto, a subtle but persistent anomaly appeared in the data. Each spacecraft was slowing down just a fraction more than it should have been, experiencing a tiny, unexplained deceleration back toward the Sun. It was as if a faint cosmic hand was gently tugging them backward. For years, this Pioneer anomaly fueled intense speculation. Could it be the first sign of modified gravity, a flaw in Einstein's theory of general relativity manifesting at the solar system's edge? Perhaps it was the gravitational pull of unseen dark matter clustering around our sun, or something even more exotic. The mystery captivated physicists, demonstrating how a deviation of mere millimeters per second squared could challenge our entire understanding of fundamental forces. The solution, when it finally came, was a masterclass in engineering humility. Meticulous analysis revealed that the primary cause was not a new law of physics, but thermal radiation pressure. The spacecraft's radioactive power sources generated heat, which radiated unevenly from the probe's bodies. This faint, lopsided photon push acted like a tiny, unseen brake, providing most of the anomalous deceleration. Yet for some, a whisper of the anomaly remains, a residual effect not entirely accounted for by the thermal model. The Pioneer story is a powerful lesson. It shows that hidden mechanisms can lurk in the most mundane of places, in the subtle interplay of heat and light on a human-made object. It reminds us that our map of gravity, so reliable here on Earth, might still hold secrets at the grand scale of our own celestial neighborhood. What other subtle gravitational quirks are influencing the paths of distant spacecraft, quietly waiting to be noticed in a stream of data? This question of hidden influence pulls our attention from the vastness of space to the very fabric of time and the strange symmetries that may govern its flow. The relentless forward march of time feels like the most undeniable fact of our existence. Yet the fundamental laws of physics, the equations governing particles and forces, are almost entirely blind to this flow. They work just as well running backward as forward. A film of two electrons colliding and repelling looks perfectly normal played in reverse. So why does our universe only play the film in one direction? The secret lies not in the laws themselves, but in a hidden condition at the very beginning of everything, a cosmic one-way street called the arrow of time. This arrow is powered by a concept known as entropy, which is essentially a measure of disorder or randomness. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Think of a drop of ink falling into a glass of water. It starts as a coherent blob, a state of low entropy, and then it spreads out, mixing evenly into the water in a high entropy state. You never see the scattered ink particles spontaneously gather back into a single drop. This inevitable slide toward disorder gives time its apparent direction. Our memories depend on it because forming a memory requires a change in your brain state, a process that increases entropy. Causality itself is built upon it, as effects always follow causes in a world where disorder only grows. The profound question is, why was the entropy of the early universe so incredibly low? Why did the cosmos begin in such an exquisitely ordered, special state, a tightly wound spring of potential that has been uncoiling ever since? For cosmologists like Sean Carroll, this is the true mystery of time's arrow. The answer may be woven into the fabric of quantum gravity and the very first moments of the Big Bang. Perhaps our universe is just one bubble in a vast multiverse, and we simply happen to inhabit a region that started with this improbable low entropy configuration. Or maybe the smooth, ordered state was a direct result of cosmic inflation, which stretched a tiny, uniform patch of space into our entire observable universe, effectively ironing out the wrinkles and setting the stage for time's one-way journey. The direction of time is not written into the laws of motion, but into the initial cosmic landscape. Why the universe was born with this specific, ordered tick is a hidden mechanism that defines our reality, forcing us to look back to the very first instant to understand the relentless flow of the present. Our universe appears to be a cosmic miracle, a place where the fundamental numbers are perfectly tuned for life. But what if this perfection is not a miracle at all, but a simple matter of statistics? The theory of eternal inflation suggests our entire cosmos might be just one bubble in an infinite, frothing sea of universes, a vast multiverse. In this picture, the Big Bang was not a unique beginning, but a local event, the nucleation of our particular bubble within a much larger, eternally expanding meta-universe. Each of these bubble universes could have its own unique set of physical laws and constants. In most, the conditions would be wildly inhospitable. Some might have gravity so strong they collapse instantly. Others might have forces too weak to ever form atoms. But in a near-infinite ensemble of possibilities, a tiny fraction of bubbles will, purely by chance, have the right numbers for stars, planets, and life. We, of course, find ourselves in one of those rare habitable pockets. This cosmic selection effect, often called the Anthropic Principle, offers a radical explanation for fine-tuning. There is no deeper reason why the cosmological constant is so small or why the proton is stable. It is simply that in a universe where they were not, no one would be here to ask the question. Proposed by physicist Andrei Lind, this vision emerges naturally from the mathematics of inflationary cosmology and finds a strange echo in string theory, which describes a landscape of perhaps 10 to the 500 possible vacuum states, each one a potential universe with its own physics. The multiverse transforms a profound mystery into a simple consequence of probability. Yet this very elegance is its greatest weakness. If other universes are permanently beyond our observational horizon, forever disconnected from our spacetime, can we ever test their existence? Critics argue this makes the idea unscientific, a philosophical retreat rather than a physical explanation. Proponents counter that the multiverse itself is a prediction of our best theories, like inflation, and that we might one day find indirect evidence, perhaps a bruise on our cosmos from a collision with another bubble in the distant past. The question is not just whether we are alone in our universe, but whether our universe is alone in a much grander reality. Are we the product of a single, special creation, or merely one fortunate outcome in an endless cosmic lottery where every possible reality is realized somewhere? This idea pushes the boundaries of science and philosophy, forcing us to consider that the hidden mechanisms shaping our existence might be operating on a canvas far larger than we ever conceived. A single, powerful radio signal pierced the noise in 1977, so remarkable that an astronomer famously scrawled "wow!" next to the data printout. This was not a whisper but a shout. For 72 seconds, it blared from a region near the constellation Sagittarius, a narrowband burst of energy that perfectly matched the profile of a potential artificial transmission. And then it vanished, never to be heard again. The wow signal remains one of the most tantalizing mysteries in the search for extraterrestrial intelligence, a perfect example of the cosmic haystack problem. We are searching for a needle we have never seen, in a haystack of unimaginable size, filled with countless other shiny objects that catch our eye. The hidden mechanism behind that signal could have been a natural one. A passing comet was later proposed, though this explanation remains contentious. It could have been a random flicker from a distant star or a glitch from a human satellite. Or it could have been something else entirely. This ambiguity fuels the entire SETI endeavor. Every time we detect a new cosmic anomaly, like the enigmatic fast radio bursts that release more energy in a millisecond than our sun does in 80 years, we face the same profound question. Are we witnessing the natural death throes of a magnetar, a highly magnetized neutron star, or are we glimpsing the engineering of a civilization so advanced its technology appears to us as natural law? The challenge is not just in hearing a signal, but in recognizing it. An advanced civilization might not use simple radio waves. Their communication could be encoded in neutrino beams, modulated gravity waves, or something we have not yet even conceived. They might use the stars themselves as lenses, or build structures on scales that block the light of entire galaxies, artifacts we could detect but not comprehend. The WOW signal is a ghost that haunts our telescopes, a reminder that the universe is filled with hidden actors. Some are natural, the clockwork of physics playing out on a grand stage. Others, perhaps, are not. Every unexplained burst of energy is a candidate, a potential sign that we are not the only ones looking up at the stars and wondering. What other messages are hidden in the static, waiting for the right moment or the right listener to be understood? The silence of the cosmos is a mystery as profound as its most violent forces. With billions of galaxies, each containing billions of stars, the universe should be teeming with life, a cacophony of alien conversations filling the void. Yet when we listen, we are met with an overwhelming and deeply puzzling quiet. This is the heart of the Fermi paradox, a question physicist Enrico Fermi famously posed over lunch one day. If they are out there, where is everybody? The sheer scale of the universe suggests that intelligent civilizations should be common, making their absence in our data a glaring contradiction. There must be a hidden mechanism, a cosmic bottleneck, or a universal law of behavior that prevents civilizations from revealing themselves or surviving long enough to be found. One of the most compelling and unsettling answers is the concept of the Great Filter. This is a hypothetical barrier, a critical step in the evolution of life that is so difficult to overcome that it effectively silences the cosmos. The filter could lie in our past. Perhaps the genesis of life itself from non-living chemistry is astronomically rare. Or maybe the jump from simple single-celled organisms to complex, multicellular life is the true miracle. If this is the case, we on Earth are the breathtaking exception, having already passed through the filter. The more haunting possibility is that the Great Filter lies in our future. It could be that almost every civilization that reaches our level of technological development soon discovers the means of its own destruction, whether through nuclear war, engineered pandemics, or a runaway artificial intelligence. The silence we hear would then be a grave warning, the echo of countless other civilizations that flashed into existence and then abruptly vanished. Alternatively, the paradox might not be about extinction, but about invisibility. A civilization just a few centuries more advanced than ours would possess technologies indistinguishable from magic, or in this case from nature. They might have moved beyond clumsy radio broadcasts, communicating through quantum entanglement or manipulating dark matter in ways we cannot perceive. Their megastructures, like hypothetical Dyson spheres harvesting the energy of stars, might be so efficient they emit no waste heat we can detect. We could be like ants in a vast forest, unaware of the hikers walking just feet away, their presence completely outside our frame of reference. This paradox forces us to confront our own cosmic context. Are we the first intelligent species to arise in this galaxy, the pioneers of a future filled with life? Are we simply lucky, one of a handful of civilizations to have made it this far? Or is the answer the loneliest of all, that we are a solitary anomaly, a flicker of consciousness in an endless, empty night? The silence is not empty. It is filled with questions about our own destiny, a hidden mechanism of limitation that defines our place in the cosmos. A hidden river of galaxies flows through the cosmos, and we are caught in its current. Our entire Milky Way, along with our local family of galaxies, is being pulled at over 2 million kilometers per hour toward a mysterious gravitational anchor in the constellation Centaurus. This colossal anomaly, known as the Great Attractor, possesses the mass of tens of thousands of galaxies, a gravitational behemoth so vast it dictates the motion of everything in our intergalactic neighborhood. Yet for decades, its true face remained hidden from us, concealed behind the Milky Way's own thick band of dust and stars, a region astronomers call the zone of avoidance. It was like trying to see a distant mountain range through a permanent, opaque fog. Our own galaxy's brilliance blinded us to the source of the pull we could so clearly feel. Through persistent observation in infrared and radio wavelengths, which can pierce the cosmic dust, a clearer picture has emerged. The Great Attractor itself, a massive supercluster of galaxies, appears to be just one waypoint in an even grander journey. The entire flow, including us and the Great Attractor, is itself streaming toward something far more immense, the Shapley supercluster, the largest known concentration of matter in our observable universe. This cosmic cascade reveals a hidden mechanism of gravity on the grandest scales. These motions are not random. They are the direct result of the uneven distribution of dark matter, the invisible scaffolding of the cosmos. Where dark matter clumps most densely, it creates gravitational wells so deep that entire superclusters of galaxies slide into them over billions of years. We are not simply expanding outward from the Big Bang, we are surfing on these immense rivers of gravitational flow, pulled by the shadows of mass we cannot directly see. The Great Attractor is a single, massive knot in gravity's tapestry, a testament to the fact that our local universe is still being shaped by structures of almost unimaginable scale. What other colossal attractors lie beyond the current limits of our vision, silently orchestrating the grand ballet of the cosmos? Our cosmic address places us in a quiet corner of the universe. We live inside the KBC void, a staggering spherical region nearly 1 billion light-years wide where the density of galaxies is significantly lower than the cosmic average. This is not our local galactic group's doing, but a feature of the large-scale structure of the cosmos, a vast bubble of relative emptiness in which our Milky Way is just one small occupant. This hidden architecture of our immediate universe has a direct and surprising consequence. It could be skewing one of the most important numbers in cosmology, the Hubble constant, which measures the current rate of the universe's expansion. The tension arises because empty regions of space expand faster than denser ones. Think of the cosmos as a rising loaf of raisin bread, where the raisins are galaxies. If you are sitting in a pocket with fewer raisins, the dough around you has less gravitational pull holding it back, so it can stretch more quickly. We are essentially measuring the expansion from inside one of these faster-moving bubbles. When we calculate the Hubble constant using nearby supernova and other local markers, we are measuring this faster local rate. But when we use the ancient light of the cosmic microwave background, which reflects the average expansion of the entire universe, we get a slightly slower value. The discrepancy between these two measurements has been a persistent headache for cosmologists. The KBC void offers a compelling, elegant solution. We are not measuring a fundamental problem with our models of the universe, but rather a local environmental effect. Our position within this grand cosmic void means our backyard is not a representative sample of the whole cosmos. This realization forces a profound shift in perspective. We are not in a special place, but we are in a specific kind of place, one that shapes our view of reality itself. How do such immense voids form in the first place? They are the natural counterpart to the dense filaments and clusters of the cosmic web, sculpted by gravity over billions of years. As dark matter pulled matter into vast sheets and nodes, it left behind these corresponding deserts, regions where the gravitational tug was weaker and galaxies failed to congregate in great numbers. The KBC void is a fossil of this process, a hidden mechanism that reminds us the universe is textured, and our local view is just one thread in a tapestry of unimaginable scale. What other cosmic illusions are created by our particular vantage point, quietly altering our perception of the laws that govern everything? Two different ways of measuring cosmic expansion are telling two different stories. One method peers into the ancient universe, studying the faint afterglow of the Big Bang known as the cosmic microwave background. This fossil light gives us a measurement of how fast the cosmos was expanding in its infancy. The other method looks at the relatively recent universe, observing the precise brightness and distance of stellar explosions called Type 1, a supernova. These two techniques should converge on the same number, the Hubble constant, which tells us the current expansion rate of the universe, yet they stubbornly refuse to agree. The numbers are off by a small but significant few percent, a discrepancy that has ballooned into a major crisis in cosmology known as the Hubble tension. This is not a minor rounding error. It is a persistent crack in the foundation of our standard model of the universe. The early universe measurement suggests a slower, more sedate expansion rate, while the local, modern measurement insists the universe is expanding faster. One of these conclusions must be wrong, or our entire understanding of cosmic history requires a fundamental rewrite. This conflict has forced cosmologists to consider astonishing possibilities. Perhaps an unknown form of energy, dubbed early dark energy, briefly surged in the universe's first few 100,000 years, altering the initial conditions before fading away. This would change the interpretation of the ancient light, potentially reconciling it with the faster modern expansion. Or maybe neutrinos, those ghostly particles that stream through everything, possess strange new properties that affected how the early cosmos evolved. They could have interacted with other particles in ways we never anticipated, subtly shifting the cosmic calculus. There is also the humbling chance that the tension stems from a hidden systematic error, a subtle miscalibration in our telescopes, or an unaccounted-for property of the supernova themselves. But with each passing year and more precise data, the discrepancy only becomes more firm, making the simple explanation of a mistake less and less likely. The Hubble tension is more than a puzzle, it is an engine for discovery. It is driving the development of powerful new telescopes and novel observational techniques, all aimed at cross-checking these measurements with independent methods. Could the ripples from merging black holes detected through gravitational waves provide a third path to the Hubble constant? Will the new James Webb Space Telescope find a flaw in our measurements of the local universe? This conflict is a stark reminder that our most trusted cosmic models are not set in stone. They are living frameworks, constantly tested by the reality they seek to describe. What hidden ingredient, what forgotten force from the dawn of time, could be casting this long shadow of disagreement over our map of the cosmos? A vast, cold shadow stains the map of the universe's first light. This is the CMB Cold Spot, a region of the cosmic microwave background that is profoundly and mysteriously colder than its surroundings. Stretching across 1 billion light-years, this cosmic chill is far larger and more intense than our standard models of inflation can easily explain. It could be a mere statistical fluke, a 1 in a million random variation in the primordial soup, but its sheer size and stark temperature drop have led cosmologists to consider a far more thrilling possibility. This cold spot might be the imprint of a cosmic texture, a scar left on spacetime from a violent phase transition in the universe's first fleeting moments. Picture the early cosmos cooling like water freezing into ice. As it underwent a fundamental shift in its state, topological defects could have formed in the fabric of reality itself. These defects are not made of matter, but are kinks and twists in the fields that permeate all of space. A texture is one such exotic defect, a knot of energy that would create a gravitational well so deep it would stretch the light passing through it, draining its energy and leaving a cold imprint on the sky we see today. If this interpretation is correct, the cold spot is not a void or a cluster of galaxies, but a fossilized wrinkle in the cosmos, a direct window into physics at energies far beyond anything our particle colliders can ever reach. It would be evidence of a grand unified phase transition, a moment when the fundamental forces of nature split apart, forever changing the character of reality. Future observatories like the Simons Observatory and the CMB S4 project are now focusing their incredible resolution on this enigmatic region. They will search for a specific polarization pattern in the light, a unique signature that would confirm the texture hypothesis. The cold spot is a ghost from the dawn of time, a hidden mechanism whose true nature could reveal that the early universe was not smooth and featureless, but etched with structures born from its most violent birth. What other primordial relics, what other cosmic scars are hidden in the faint light of creation, waiting to tell their story? Spacetime itself may be threaded with cosmic defects, unimaginably thin strands of pure energy left over from the universe's fiery birth. These are cosmic strings, theoretical one-dimensional scars stretching across the cosmos, formed when the fundamental forces of nature underwent their first great separation. As the cosmos cooled, it may have undergone a phase transition not unlike water freezing into ice. But when a field governing the universe freezes, it can freeze in different directions, and where those different domains met, a flaw could have been trapped in the fabric of reality, a crack that never healed. A cosmic string is not a string in the everyday sense. It is a flaw in spacetime, a rip so dense that a single inch of it could weigh more than a mountain. Yet it would be thinner than a proton, a thread of incredible tension slicing through the universe at nearly the speed of light. If one passed through you, you would likely never know, as its width is subatomic, but its gravitational influence would be profound. These cosmic threads would warp the space around them, acting as perfect gravitational lenses. They could create double images of distant galaxies, or even produce razor-straight lines of twin quasars in the sky. As they vibrate and oscillate, they would ripple the fabric of spacetime itself, generating a background hum of low-frequency gravitational waves, a chorus from the dawn of time. Their most dramatic signature would be a step-like discontinuity in the cosmic microwave background, a sharp temperature jump between two regions of the sky where a string's immense gravity has sheared the primordial light. Their existence is a key prediction of many grand unified theories, and finding one would be like discovering a fossil from the universe's first trillionth of a second, a time far before the formation of any particle we can create in a lab. How do we listen for the vibrations of these primordial threads? The answer pulls us toward a new way of sensing the cosmos, one that feels its deepest tremors not with light, but with the very stretching of space. The black holes we know are born from the dramatic deaths of massive stars, but what if a far more ancient and secretive kind of black hole exists? Primordial black holes are a hypothetical population that could have formed in the first chaotic second after the Big Bang, when the universe was a dense, seething cauldron of energy. In that extreme environment, random fluctuations in density could have been so intense that pockets of space simply collapsed under their own weight, pinching off into black holes without the need for a single star. These relics would be cosmic phantoms, ranging in size from a small asteroid to many times the mass of our Sun, scattered throughout the cosmos and completely invisible to our telescopes. If they are real, they could solve one of cosmology's greatest puzzles, forming a significant portion of the dark matter that holds galaxies together. We would be living in a universe permeated by these ancient gravitational pits, their collective pull shaping the cosmos from the shadows, how would we ever find something so dark and elusive? Their presence would only be betrayed by subtle gravitational effects. When a primordial black hole passes in front of a distant star, its gravity acts as a lens, bending the starlight and causing the star to temporarily brighten in a phenomenon called microlensing. Astronomers are meticulously scanning the skies for these telltale flashes. Others listen for the faint, high-frequency chirp of gravitational waves, which could be emitted when two of these ancient objects spiral into each other and merge. The possibility reshapes our entire origin story for black holes. The supermassive giants at the centers of galaxies might not have grown slowly over time. Instead, they could have started as hefty primordial seeds, born large in the universe's infancy, providing a head start for their eventual growth into the monsters we observe today. This idea connects the very old with the very dark, suggesting that the hidden architecture of our reality might be built upon the gravity of countless silent fossils from the dawn of time. What if the darkness we call empty space is actually studded with these primordial artifacts, a hidden population of gravitational ghosts from the first moment of everything? Perhaps the Big Bang was not a true beginning, but merely the latest in an endless cycle of cosmic rebirth. The Echperotic universe model dares to propose exactly that, painting a picture of creation without a singular, explosive origin. This radical idea emerges from the depths of string theory, suggesting our entire three-dimensional universe is a membrane or a brain floating within a higher dimensional space. In this hidden reality, our cosmos is not alone. It exists alongside another parallel brain, separated by a gap so tiny it defies measurement. The engine of creation is not a mysterious Inflaton field, but the slow, inevitable dance of these colossal membranes. They drift toward each other over eons, drawn by a force across the extra dimensions until they finally collide. That collision, a universe-shattering event of unimaginable power, is what we perceive as the Big Bang. It was not an explosion from a point, but a fiery rebirth ignited by the touch of another world. In this model, the universe is cyclic. After the collision, the brains bounce apart, filled with the energy and matter of the new cosmic cycle. They then slowly drift apart, only to be drawn together once more, setting the stage for the next collision, the next Big Bang, in an eternal rhythm without beginning or end. This elegant mechanism sidesteps the troubling initial singularity, that point of infinite density where our known laws of physics break down. It also naturally explains the smoothness and flatness of our universe, not through a period of hyper-fast inflation, but through the stretching and smoothing of the brains as they move apart before a collision. The most tantalizing clue that could distinguish this model from standard inflation lies in the pattern of primordial gravitational waves. An echperotic collision would produce a very different signature in the cosmic microwave background and the gravitational wave background than inflationary models predict. It would create a spectrum of ripples in spacetime that our next-generation observatories might one day detect. While this cyclic vision of the cosmos remains a fringe theory, it represents a profound class of hidden mechanisms that challenge our most fundamental story. It asks us to consider that our entire cosmic history, from the first light to the last star, might be just one chapter in an infinite, repeating saga. What if our universe is not a unique creation, but an echo in an endless hall of mirrors? Hidden within the mathematics of our most ambitious theory lies a cosmic library of almost infinite possibilities. String theory, an attempt to weave gravity into the quantum fold, proposes that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. The specific vibration of each string determines the properties of the particle it manifests, from a quark to a photon. But for this elegant symphony to produce the universe we know, the theory requires more than the three spatial dimensions we experience. It demands extra dimensions curled up into shapes so small we can never perceive them directly. The way these extra dimensions fold and twist, a process known as compactification, is the master key. Each possible configuration, each distinct geometric shape for these hidden dimensions, corresponds to a different vacuum state, a unique set of stable conditions with its own specific laws of physics and fundamental constants. The result is not one universe, but a nearly infinite landscape of potential universes, a vast and silent multiverse where the strength of gravity, the mass of an electron, and even the number of dimensions could be completely different. Our cosmos, with its particular and seemingly fine-tuned constants, is just one fertile valley in this sprawling cosmic terrain. We are not living in the only possible universe, but simply in a universe that allows for our existence. This landscape offers a profound, if controversial, answer to the question of why our physical laws are so hospitable to life. There is no deeper reason, no grand design. In a library containing every possible book, it is no surprise to find one written in a language we can read. Yet this very power is the theory's greatest weakness. With a landscape of 10 to the 500 possible vacuum states, virtually any physical outcome becomes possible somewhere. This staggering lack of predictive power leads critics to argue that string theory, in its current form, is not a testable scientific theory but a philosophical framework. How can we ever navigate this cosmic atlas to find our own entry? The search is for a principle, a hidden rule that might guide the universe's selection of one stable vacuum over another, perhaps through the mechanism of cosmic inflation itself. Are we the product of a random quantum roll of the dice in the first instant of time, or does a deeper, more fundamental law point the way to our particular cosmic address? A single atom can be in two places at once, spinning both clockwise and counterclockwise, a ghostly superposition of possibilities. Yet the world we see is solid, definite, and predictable. The chasm between these two realities is the measurement problem, one of the most profound and unsettling gaps in all of physics. Why does the mere act of looking force the quantum world to make up its mind? Erwin Schrödinger famously illustrated the absurdity with his cat. A feline is sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers and breaks the vial, killing the cat. According to quantum rules, the atom exists in a superposition of both decayed and not decayed states until someone opens the box and looks. This means the cat, by extension, must be both alive and dead, a blurred mixture of two realities, until observation collapses the wave function into a single outcome. This is not a statement about animal cruelty, but a stark challenge to our understanding of reality itself. What magical property does a conscious observer possess that can force the universe to choose? The most practical answer lies in a hidden mechanism called decoherence. A quantum system left perfectly isolated can maintain its superposition, but in the real world it is constantly bombarded. Every stray photon, every passing air molecule, every faint gravitational tug constitutes a measurement. These relentless interactions with the environment effectively force the system to pick a state, leaking information about its configuration into the wider world. The quantum weirdness is not destroyed, but it becomes so scrambled and spread out across the environment that it is irrecoverably lost for all practical purposes. The cat is never truly both alive and dead because the environment inside the box is constantly measuring the system, forcing a definite outcome long before a human ever lifts the lid. Decoherence explains how the classical world emerges from the quantum one without needing a conscious observer. Yet some physicists argue this only pushes the problem back a step. When does the environment itself, which is made of quantum particles, stop being in a superposition? This line of thinking leads to more radical proposals like objective collapse models, which suggest there is a fundamental, non-quantum limit to superposition, perhaps related to gravity. When a system becomes too massive, its own gravity might force it into a definite state. Others still ponder the role of consciousness, a deeply controversial idea that suggests awareness itself is the ultimate catalyst that resolves possibility into actuality. This is not mysticism, but a recognition that our description of reality is incomplete. The measurement problem is the silent hinge between the quantum weirdness that underpins everything and the stable universe we inhabit. Its resolution will not just tell us why a cat is either alive or dead. It will reveal the hidden mechanism that constructs our concrete reality from a foundation of ghostly potential. At the very heart of a black hole, our map of reality tears in two. General relativity, our master theory of gravity, predicts a final destination known as a singularity, a point of infinite density where all the known laws of physics simply cease to function. It is a place where space and time as we understand them come to a complete and utter end, a mathematical and conceptual abyss hidden safely behind the event horizon's ultimate veil. This prediction is not just a curiosity, it is a screaming alarm that our understanding is incomplete, a clear signal that we need a deeper theory, one that can weave gravity together with the quantum world. What could possibly replace such a monstrous infinity? Some of the most promising candidates for a theory of quantum gravity offer startling alternatives. Loop quantum gravity, for instance, suggests there is no singularity at all. Instead, the crushing collapse of matter might hit a quantum wall of resistance, a sort of cosmic bounce where the immense gravitational pressure is transformed into a rebounding force, potentially giving birth to a new universe in a hidden cosmic cycle. String theory proposes another exotic solution, the fuzzball. In this vision, the black hole's core is not a single point, but a tangled, vibrating ball of fundamental strings, a quantum knot of such complexity that it has a definite, albeit tiny, size. This fuzzy sphere would have no sharp singularity, replacing the infinite with a bustling, finite structure governed by quantum law. The true nature of this hidden core is not just an academic exercise. It dictates the ultimate fate of everything that falls into a black hole and holds the key to unifying the two great pillars of modern physics. The quest to understand what lies at a black hole's heart is more than a search for answers. It is a journey to the very edge of meaning, pushing our imagination to its limits to glimpse the final laws that orchestrate our cosmos. Even the experience of warmth is not a universal truth. Drift through the void of what we call empty space, and you will find only a profound, deep cold. But if you were to fire your engines and accelerate, something remarkable would happen. You would begin to feel a gentle heat, as if bathed in a faint, ethereal glow. A thermometer would confirm it. You are detecting particles, a warm bath of radiation where moments before there was nothing. This is the Unruh Effect, a hidden mechanism where motion itself conjures reality from the vacuum. The key is acceleration. For an observer moving at a constant velocity, the vacuum remains empty and silent. But for the one who is accelerating, the very act of pushing through space-time disrupts the quantum fields that fill it. The gentle glow you feel is a direct result of your own motion, a quantum mirage made real by your journey. It is as if the relentless quantum jitter of the vacuum, the same virtual particles that flicker in and out of existence, gets stretched and amplified by your acceleration. What was a brief, unnoticeable fluctuation for a stationary observer becomes a real, detectable particle for you. Your state of motion literally determines what you perceive to be real. This bizarre phenomenon is more than a theoretical curiosity. It provides a profound bridge between Einstein's theory of relativity and the strange world of quantum mechanics, showing that the concept of a particle is not absolute but deeply relative. It depends entirely on your path through the cosmos. The implications ripple outward, touching the most extreme environments we know. At the edge of a black hole, the immense gravitational pull creates a form of acceleration. The Hawking radiation that slowly evaporates a black hole is a cousin to this Unruh glow, both born from the way different observers experience the quantum vacuum. This forces us to confront a radical idea. The vacuum of space is not a static emptiness. It is a dynamic, seething medium whose true nature is only revealed through interaction. What we call nothing is in fact a plenum of potential, a stage where the script of reality is written by the motion of the players themselves. How many other aspects of our world are not fixed properties, but fleeting appearances conjured by our own journey through the cosmos? Even nothingness can push back. Place two flawless, uncharged metal plates so close together in a vacuum that they are almost touching, a gap smaller than a single wavelength of light. According to classical physics, absolutely nothing should happen. But in the quantum world, this emptiness is a storm. A constant sea of virtual particles flickers into and out of existence, creating a fluctuating pressure against all surfaces. Between the plates, however, only certain wavelengths of these quantum fluctuations can fit. Outside the plates, all wavelengths are free to churn. This imbalance creates a relentless push from the outside that is stronger than the pressure from within the narrow gap, forcing the plates together with a faint but measurable force. This is the Casimir Effect, a hidden quantum hand that reaches out from the void. We have measured this ghostly attraction in laboratories, confirming that the vacuum is not a passive stage but an active participant in the dance of reality. This quantum pressure is not just a theoretical curiosity. It presents a major challenge for engineers building microscopic machines and nanoscale devices, where these phantom forces can cause components to unexpectedly stick together, a phenomenon known as stiction. Yet this same effect also points toward a future of quantum vacuum engineering, where we might one day learn to manipulate these vacuum fluctuations to our advantage, perhaps to create frictionless bearings or new forms of propulsion. The Casimir force is a whisper from the quantum world, a tangible pull generated by the frantic activity of empty space itself. It proves that the void is not empty but full of a latent power, a pressure inherent to existence. What other invisible quantum hands are at work in the microscopic realm, subtly shaping the world just beyond our direct perception, waiting to be harnessed? Our universe's laws seem to have been set with life in mind. If the force of gravity were just a fraction stronger, the cosmos would have collapsed back on itself long ago. If the nuclear forces were a bit weaker, not a single atom beyond hydrogen could have formed. This uncanny fine-tuning has led to a profound and sometimes controversial line of reasoning known as the Anthropic Principle. In its simplest form, it states that we observe the universe to be a certain way because if it were not, we would not be here to observe it. It is a cosmic selection effect, a logical answer to why we find ourselves in such a hospitable corner of reality. This principle offers a powerful framework for tackling some of our greatest puzzles, like the impossibly small value of the cosmological constant. The vacuum energy should be colossal, yet it is almost zero. The anthropic answer is startlingly simple. In a universe where it was any larger, galaxies and stars could never have coalesced. We exist, therefore we must live in one of the rare universes where this constant is negligibly small. This logic finds a natural home in the concept of the multiverse. If an infinite number of universes exist, each with its own random set of physical constants, then it is no surprise that we find ourselves in one of the vanishingly few that permits complex chemistry and conscious life. We are the winners of a cosmic lottery we never knew we entered, yet this explanation feels deeply unsatisfying to some. It swaps a miracle of design for a statistical fluke, moving the question of why our universe is bio-friendly from physics to metaphysics. Does the Anthropic Principle point toward a vast, aimless multiverse, or could it hint at something more, a deeper teleology or purpose woven into the fabric of existence? This hidden logic forces a bridge between the cold equations of cosmology and the warm, messy reality of biology, asking us to consider whether the cosmos itself has a hidden bias, a silent inclination toward life. Your own consciousness, the very feeling of being a person reading these words, could be the product of a momentary cosmic accident. In a universe that persists for an unimaginable eternity, random quantum fluctuations can occasionally assemble particles into any configuration, no matter how complex. Given enough time, these random jitters could spontaneously form a fully self-aware brain, complete with false memories of a past that never happened and sensory impressions of a world that does not exist. This ghostly entity is known as a Boltzmann brain, named for the physicist Ludwig Boltzmann, and its theoretical possibility creates a terrifying paradox. If our cosmos is destined for an eternal, quiet future, then the number of such random, disembodied brains should vastly outnumber the number of real, evolved beings like us who arose from billions of years of structured cosmic history. Statistically, you and I should be those fleeting, isolated hallucinations, adrift in an endless void, rather than the products of a continuous, ordered reality. This is not just a philosophical puzzle, it is a direct challenge to our best models of cosmology. A universe that expands forever, dominated by dark energy, provides the infinite time necessary for these freak fluctuations to become not just possible, but overwhelmingly probable. The fact that we observe a coherent, structured universe around us, with a consistent history written in starlight and fossils, suggests something is profoundly wrong with that picture. Either our universe is not eternal and will eventually end in a way that prevents such fluctuations, or there is something special about its initial low entropy state that makes our ordered existence far more likely than a solitary, random mind. Perhaps the answer touches on the nature of consciousness itself. Could a truly isolated brain, born of chaos, ever be considered conscious in the same way we are? Or does genuine awareness require a rich, interactive history with a real world? The Boltzmann brain paradox forces us to question the most fundamental assumption we have, that we are real beings in a real cosmos. It asks why the universe seems so sturdy and continuous when the raw math of probability suggests we should be nothing more than transient ghosts in an infinite, silent machine. The cosmos presents us with a mystery of impossible synchrony. Look in any direction and the ancient afterglow of the Big Bang, the cosmic microwave background, shows a nearly identical temperature, a uniform warmth that defies common sense. Regions of space on opposite sides of the observable universe were simply too far apart for light or heat to have ever traveled between them in the time available since the beginning. They were causally disconnected, forever out of touch, like two ships sailing on an ocean so vast they could never signal one another. Yet, mysteriously, they both settled on the exact same temperature, as if by some unspoken cosmic agreement. This is the horizon problem, a deep puzzle about why the universe looks so similar everywhere. How could these distant realms have coordinated their properties without ever being in contact? The leading answer is cosmic inflation, a period of unimaginably rapid expansion that stretched a single, tiny, homogeneous patch of the early universe into a volume far larger than our entire observable cosmos. This process ironed out all the wrinkles, ensuring that everything we see today originated from a region that was once intimately connected, a place where everything had time to mix and reach a common temperature before being blown apart. But this elegant solution only pushes the mystery one step further back. What were the conditions before inflation began? What was the nature of that initial, perfectly uniform patch? Was it a state of thermal equilibrium from an even earlier epoch, or did it emerge from a quantum fluctuation in a deeper, more fundamental void? The horizon problem forces us to confront the ultimate origin of cosmic order, suggesting a hidden causal structure that bound the infant universe together long before the forces we know took hold. This points toward a reality where our entire cosmic history is just a chapter in a much longer story, a story whose first pages are still missing. What was the universe like before it was a universe, and what hidden mechanism wrote the first law of cosmic uniformity into its fabric? Geometry itself seems to hold a cosmic secret. The space we inhabit is not merely a passive container, it has a shape, and the shape of our universe is, for all practical purposes, perfectly flat. This is not a metaphor. It means that on the grandest scales, parallel laser beams will never meet or diverge, and the angles of a triangle will always add up to exactly 180 degrees. Such geometric perfection, however, presents a profound puzzle known as the flatness problem. For the universe to be this flat today, its initial density in the first moments of the Big Bang had to be fine-tuned to an almost impossible precision, balanced to within 1 part in a million trillion. If the density had been even slightly higher, the universe would have collapsed back on itself in a swift big crunch. If it had been slightly lower, it would have expanded so rapidly that no galaxies could ever have formed. The odds of achieving this balance by chance are astronomically small, as if you balanced a pencil on its tip for 14 billion years and it never fell over. So why does our cosmos exhibit this incredible geometric simplicity? The leading explanation is, once again, cosmic inflation. That brief, violent burst of expansion would have acted like a cosmic iron, stretching any initial curvature in spacetime until it appeared perfectly flat, just as blowing up a balloon makes its surface look flatter and flatter from the perspective of an ant crawling on it. Inflation provides a natural mechanism to erase the original wrinkles, delivering the flat universe we observe, yet this only pushes the mystery one step deeper. What was the universe like before inflation? Did it possess some inherent geometric simplicity from its very origin? The answer might lie in the quantum gravitational realm, where the concepts of space and time themselves break down. Perhaps in that first fleeting moment, the universe was born from a quantum fluctuation that naturally favored a flat geometry. Or maybe our universe is part of a much grander cyclic story, as proposed by the Echperotic model, where each collision and rebirth of brains naturally produces a flat, smooth cosmos, avoiding the need for a special beginning altogether. This hidden geometric perfection is not just a curious fact, it is fundamental to our cosmic fate. A flat universe dictates a specific destiny, one that will continue expanding forever, growing ever colder and more diffuse, leading toward that final state of profound isolation. Why the foundational shape of reality is so simple and balanced remains one of cosmology's most elegant mysteries. a silent testament to a hidden mechanism that set the stage for everything that followed. Our universe seems to be missing a fundamental piece of its magnetic personality. Every magnet we have ever found, from a simple refrigerator magnet to the entire planet Earth, comes with two inseparable poles, a north and a south. Break one in half and you do not get isolated poles, you simply create two new, smaller magnets, each with its own north and south. This is a basic, observed fact of nature. Yet our most ambitious theories of physics insist this cannot be the whole story. Grand unified theories, which aim to merge the electromagnetic, weak and strong nuclear forces, make a startling and firm prediction. In the extreme energies of the early universe, a new kind of particle should have been forged, a magnetic monopole. This would be a particle with only one magnetic charge, a solitary north or a lonely south, wandering through the cosmos as a stable, heavy relic of creation. The problem is we have never seen one. Not a single confirmed magnetic monopole has ever been detected despite decades of searching. Their predicted abundance is so high that we should be tripping over them, with a density that would make them more common than protons. So where did they all go? The most elegant solution is cosmic inflation. That brief, violent stretching of spacetime would have diluted the primordial soup of particles to an incredible degree, scattering the monopoles so far and wide that they effectively vanished from our observable universe. Their profound absence is actually a powerful piece of evidence for inflation itself. Yet the search continues because finding just one monopole would be a discovery of monumental importance. It would be direct proof that the fundamental forces were once united, a frozen fossil from the universe's first moments of symmetry. It would reveal a hidden simplicity within electromagnetism, showing that electricity and magnetism are even more deeply connected than we thought, two sides of a coin we have only ever seen one face of. Are these solitary magnetic ghosts drifting through the vast emptiness between galaxies, or trapped deep within ancient rocks? Their elusive nature continues to constrain our theories, a silent reminder that our cosmic inventory is still missing a key that could unlock a new chapter in physics. The neutron's perfect neutrality hides a cosmic secret, deep within its core where quarks dance under the influence of the strong nuclear force. A profound symmetry should be broken, yet somehow it remains intact. This is the strong CP problem, a hidden mechanism that keeps our very atoms stable. The laws of quantum chromodynamics, which govern how quarks bind together, technically allow for a process that would violate the combined symmetries of charge and parity. In simple terms, this would make the neutron ever so slightly electrically lopsided, giving it what is called an electric dipole moment. You could think of a neutron as a tiny, perfect sphere. This violation would distort it, creating a positive end and a negative end. Our most sensitive experiments have searched for this distortion, and they have found nothing. The neutron's electric dipole moment is not just small, it is vanishingly small, a value so close to zero it seems to have been tuned by an invisible hand. This is deeply puzzling. Why does the strong force, the most powerful force in nature, so meticulously preserve this symmetry when its own rules say it should not? The fine-tuning required is absurdly precise, suggesting a hidden mechanism is at work, protecting the integrity of matter itself. The most elegant solution introduces a new particle, the action. This hypothetical entity would act as a cosmic correction factor, a field that dynamically adjusts to cancel out any CP-violating effects in the strong force, naturally explaining the neutron's perfect neutrality. The action is not just a convenient fix, it is a compelling candidate for the dark matter that permeates the cosmos. These ghostly particles, if they exist, would be incredibly light and abundant, streaming through you right now without a trace. They could have been produced in vast quantities in the hot early universe, forming the invisible scaffolding upon which galaxies were built. This single puzzle, therefore, bridges the world of the infinitesimally small with the grand scale of the cosmos. The strong CP problem forces us to consider that a hidden symmetry, enforced by an unseen particle, is woven into the fabric of reality, ensuring the stability of atomic nuclei and perhaps even holding the universe together. What other invisible guardians are silently maintaining the delicate balance of our existence? The very field that gives particles their mass could be the agent of our ultimate destruction. The Higgs field, which permeates all of space and makes our structured reality possible, might not be resting in its true, lowest energy state. Instead, it could be perched in a false vacuum, a state of temporary but profound stability, like a ball resting in a small dip on the side of a vast, steep valley. For now, everything seems solid and permanent, but a quantum event, a random fluctuation of immense energy, could theoretically nudge this field over the ledge, triggering a catastrophic phase transition. A bubble of true vacuum would then form, expanding at the speed of light in all directions. The fundamental laws of physics would change instantly at its wall. The forces that hold atoms together would simply cease to function. Every star, every planet, every molecule in its path would dissolve into a formless, unrecognizable state. The universe as we know it would be erased, not with a bang, but with a silent, all-consuming wave of transformation. Current calculations suggest this event is extraordinarily unlikely to occur for many billions of years, but the uncertainties are immense. The stability of our cosmos hinges on the precise mass of the top quark and the Higgs boson itself, numbers we are still refining. This hidden mechanism of vacuum metastability paints a startling picture of our cosmic home. We may not be living in a permanent, safe universe, but in a temporary and profoundly fragile one, a beautiful edifice built on a foundation that could, at any quantum moment, collapse. Why would the universe be built on such a precarious ledge? The answer may lie in the conditions of the Big Bang itself, a frozen accident that left the cosmos in a state of suspended animation. Or it could be a clue that our understanding of physics at the highest energies is fundamentally incomplete. This cosmic instability adds a new dimension to our search for a final theory, transforming it from a purely academic pursuit into a race to understand the ultimate fate of everything we are and ever will be. What other hidden instabilities are woven into the fabric of reality, waiting for a single, random trigger to rewrite the rules of existence? The outer stars of a spiral galaxy race around its core at a breathtaking and impossible speed. According to the established laws of gravity and motion, these distant suns should be moving far more slowly, like planets on the fringes of a solar system. Their velocity is so great that the collective gravity of all the galaxy's visible stars, gas, and dust should be utterly incapable of holding them in orbit. They should be flung out into the dark intergalactic voids, yet they remain, tracing their frantic, stable paths. This glaring contradiction between prediction and observation is the galaxy rotation problem, a profound clue that our inventory of the cosmos is missing its most crucial ingredient. The discovery of this anomaly is credited to astronomer Vera Rubin and her colleague Kent Ford. In the 1970s, they meticulously mapped the rotation curves of spiral galaxies, graphing how the orbital speed of stars changes with their distance from the galactic center. The results were unequivocal and shocking. Instead of the predicted steep decline in speed, the rotation curves remained flat. Stars on the outer edge were moving just as fast as those near the core. The only logical conclusion was that each galaxy is embedded within a massive, invisible halo of something that exerts a gravitational pull, a shadowy substance we now call dark matter. This hidden mass does not glow, absorb, or reflect light in any way. It is completely transparent to every form of electromagnetic radiation we can muster. We cannot see it, but we can feel its immense gravitational grip on everything we can see. It is the unseen architect of galactic structure, a framework that dictates the motion of stars on a scale we are only beginning to comprehend. In response to this puzzle, some physicists have proposed an alternative path, suggesting the problem lies not with missing matter, but with our understanding of gravity itself. Modified Newtonian dynamics, or MUND, posits that the force of gravity behaves differently at the extremely low accelerations found in the outer reaches of galaxies. It is a radical idea that attempts to rewrite Newton's laws to fit the observed rotation curves without invoking an invisible component. While MUND can successfully explain the motions within many individual galaxies, it struggles to account for all the evidence. The gravitational lensing of galaxy clusters, where the light from distant objects is bent by immense unseen mass, and the precise patterns in the cosmic microwave background, both point overwhelmingly toward the existence of a collisionless, non-luminous form of matter. Dark matter remains the leading solution, the hidden mechanism that not only solves the rotation problem, but also explains how galaxies formed in the first place. In the early universe, the gravitational wells created by dark matter acted as seeds, drawing in ordinary gas to ignite the first stars and build the majestic structures we observe today. How does this unseen matter orchestrate the grand ballet of a galaxy? It provides the gravitational skeleton, the invisible hand that guides billions of stars in their silent, swirling dance through the cosmos, a constant reminder that most of the universe is made of something we cannot see. A spiral galaxy's brightness and its speed of rotation are locked together in a cosmic secret handshake. The Tully-Fisher Relation reveals that the more luminous a spiral galaxy is, the faster its stars spin around the galactic center. This is not a loose trend, but a remarkably tight and precise correlation observed across the universe, a fundamental scaling law that any successful theory of galaxy formation must explain. It is as if every galaxy, regardless of its individual history, agrees to follow a single, elegant rulebook for how light and motion must balance. The sheer consistency of this relation is a profound clue, pointing toward a hidden mechanism that synchronizes the visible and the invisible. The rotation speed is dictated by the total mass, dominated by the immense, unseen halo of dark matter. The luminosity, however, comes from the stars, the ordinary baryonic matter that has condensed and ignited within that dark gravitational well. The Tully-Fisher relation, therefore, is not just about stars or dark matter alone. It is a direct reflection of their intricate cosmic partnership. It tells us that the process of galaxy formation is not random chaos, but a regulated dance. The amount of ordinary gas that can cool, collapse, and form stars is intimately governed by the properties of the dark matter halo that cradles it. A more massive halo spins faster and can gather more gas, leading to the formation of more stars and greater luminosity. This creates the clean, predictable relationship we observe. Why does this correlation hold with such stunning precision across billions of years and countless galaxies? The answer is written in the feedback loops of galactic evolution. Supernova explosions and active galactic nuclei can heat or expel gas, preventing too many stars from forming and thus maintaining the balance. This hidden scaling law is a master key for cosmologists, allowing them to measure the distances to far-off galaxies simply by observing their rotation, and serving as a critical test for the most sophisticated supercomputer simulations of the cosmos. It forces our virtual universes to obey the same real-world rules, revealing whether we truly understand how the dark framework and the luminous structures co-evolve. What other universal laws of galactic architecture are waiting to be discovered, silently governing the growth and destiny of every island universe in the sky? The most energetic particles in the universe are cosmic bullets, protons accelerated to speeds a hair's breadth from light itself. They should not be able to travel very far. As these ultra-high energy cosmic rays journey across the cosmos, they are constantly running into the faint, cold glow of the cosmic microwave background, the leftover heat from the Big Bang. Each photon in this ancient light is like a tiny, nearly stationary pebble. For a proton traveling with unimaginable energy, hitting one of these pebbles is a catastrophic event. The collision is so violent it spawns new particles, primarily pions, draining the proton's energy in a process predicted by physicists Greisen, Zatsepin, and Kuzmin. This creates a fundamental roadblock, a theoretical limit known as the GZK cutoff. Beyond a certain energy, no cosmic ray from a distant source should be able to reach us. Their journey should be cut short after a mere 100 million light-years or so, a tiny fraction of the cosmic scale. Yet, when we look up with our most sensitive detectors, we see them. A handful of these impossibly energetic particles punch through, carrying more energy than a professionally thrown fastball, all concentrated into a single subatomic point. Their existence is a profound mystery. Are they coming from incredibly powerful and relatively nearby sources, cosmic accelerators in our own galactic neighborhood that we have yet to identify? Or does their survival hint at something far more radical, a crack in the very foundation of our understanding of spacetime? Some theories suggest a possible violation of Lorentz invariance, a cornerstone of Einstein's special relativity. This principle dictates that the laws of physics are the same for all observers moving at constant speed, and it sets the cosmic speed limit of light. If this invariance is not perfect, if it breaks down at these extreme energies, then the calculations for the GZK cutoff might be wrong. These particles could be playing by different rules, allowing them to travel unimpeded across vast cosmic distances. This hidden interaction between the rarest particles and the oldest light is a brutal stress test for our most fundamental theories. It forces us to ask whether the universe has secret loopholes, hidden passages that allow information and energy to flow in ways we thought were forbidden. What colossal engines in the void are capable of firing such devastatingly powerful shots? And what do their messages tell us about the true laws governing reality's ultimate extremes? Our entire cosmic model rests on a single, sweeping assumption, the cosmological principle. This foundational idea states that on the very largest scales, the universe is both homogeneous and isotropic. It looks the same in every direction, and no particular place is special. This belief in cosmic uniformity is the bedrock upon which we built our understanding of the Big Bang and the expansion of space. Without it, our equations would crumble and our maps of cosmic history would be meaningless. But what if this principle is not a fundamental truth, but merely a convenient approximation, a local illusion? Recent sky surveys have begun to uncover colossal structures that defy this assumption. Astronomers have mapped cosmic filaments and superclusters of galaxies so vast they stretch for billions of light-years, forming a grand cosmic web of unimaginable scale. The Hercules Corona Borealis Great Wall, for instance, is a gravitational structure so enormous it challenges the very definition of large scale. If the universe is truly uniform, such immense features should not exist. They appear as cosmic continents in a sea that is supposed to be smooth, The presence of these giant formations forces a difficult question. Are we seeing the limits of the cosmological principle, a sign that the universe possesses a hidden grain and texture we never anticipated? One possibility is that we are living in a special region, a cosmic anomaly that merely looks average from our limited vantage point. Our entire observable universe could be just one bubble in a far grander and more varied cosmos, a place where the rules are subtly different. This would mean the laws of physics we measure are not universal constants, but local bylaws relevant only to our own cosmic neighborhood. Alternatively, these giant structures could be pointing toward new physics, a modification to gravity or a more complex history of inflation that left behind these primordial imprints. The drive to resolve this mystery is fueling the most ambitious astronomical projects in history. Telescopes are now conducting enormous surveys of the sky, meticulously plotting the three-dimensional positions of millions of galaxies to see if the universe truly plays by the same rules everywhere. Is the grand stage of reality truly uniform, or are we just beginning to see the hidden architecture, the colossal walls and voids that define a cosmos far more complex and structured than we ever dreamed? Trillions of these ghostly particles are streaming through your body every second, leaving no trace of their passage. Neutrinos are the universe's most aloof elementary particles, entities so reluctant to interact that they can pass through light years of lead without a single collision. Born in the hearts of stars, in the fury of supernova, and in the aftermath of the Big Bang itself, they are cosmic messengers carrying information from the most violent events in creation. Yet for all their abundance, their fundamental nature remains one of physics' most profound secrets. We know they possess a vanishingly small mass, but not how much. We know they come in three types or flavors: electron, muon, and tau, and that they constantly morph from one to another in a quantum phenomenon called oscillation. But their absolute masses and a deeper question about their identity remain locked away. The most tantalizing mystery is whether the neutrino is its own antiparticle, a hypothetical entity known as a Majorana particle. If this is true, it would mean that a neutrino and an antineutrino are one and the same, a concept that shatters our conventional understanding of matter. This single property could unravel the universe's original sin, the matter-antimatter asymmetry. A process called neutrinoless double beta decay would become possible, where two neutrons in a nucleus could turn into two protons without emitting any neutrinos, effectively demonstrating that the neutrino annihilated itself. Experiments deep underground, shielded from cosmic rays, are now hunting for this ultra-rare event. Their goal is to catch a glimpse of a nucleus transforming in absolute silence, a discovery that would rewrite the standard model of particle physics. These ghostly particles are not just passive spectators. Their tiny masses have subtly shaped the cosmic web, influencing how galaxies clustered in the early universe. The answers they hold are buried in the data of next-generation detectors, machines of incredible sensitivity waiting to listen to the faintest whisper from the atomic nucleus. What cosmic truth will we uncover when we finally corner these phantoms of the particle world? A star's final breath is governed by a single, unbreakable number. The Chandrasekhar Limit is the ultimate boundary for a white dwarf, the Earth-sized corpse of a star like our Sun, setting its maximum possible mass at 1.4 times that of our own star. Beyond this threshold, no force in the universe can prevent a catastrophic gravitational collapse. The mechanism that enforces this cosmic rule is not fire or radiation, but a bizarre quantum law known as electron degeneracy pressure. In the incredibly dense core of a white dwarf, electrons are packed together, stripped from their atomic nuclei, and squeezed into a frantic quantum sea. The Pauli exclusion principle states that no two electrons can occupy the same quantum state. They simply refuse to be crammed into the same space, and this stubborn quantum resistance creates an outward pressure that counteracts the star's immense inward pull of gravity. It is a silent, invisible standoff between the rules of the quantum world and the relentless force of gravity. For a solitary white dwarf, this battle ends in a permanent stalemate, allowing it to cool slowly into a dark cinder over trillions of years. But a white dwarf in a binary system faces a far more dramatic fate. If it begins to siphon material from its companion star, its mass slowly increases. With every stolen ounce, gravity's grip tightens, compressing the stellar core further. The electrons are forced to move faster and faster, approaching the speed of light, but even their frantic motion has a limit. Once the scale tips past 1.4 solar masses, electron degeneracy pressure shatters. In less than a second, gravity wins. The core implodes, and in a furious rebound, the entire star is torn apart in a thermonuclear inferno, a Type 1, a supernova. These explosions are so phenomenally consistent in their peak brightness that they act as standard candles, cosmic mileposts that allowed us to discover the accelerating expansion of the universe and the existence of dark energy. Yet this elegant limit is not perfectly rigid. The presence of rapid rotation or strong magnetic fields can push the critical mass slightly higher. Furthermore, as the density soars in the final moments before collapse, the effects of Einstein's general relativity become crucial, subtly altering the point of no return. This hidden quantum boundary does more than just mark a star's death. It forges the elements that make life possible and provides the very tools we use to map the cosmos. How many other invisible thresholds are silently waiting in the hearts of stars, ready to rewrite the fate of a galaxy? Deep within the cosmic web of galaxies lies a phantom signature, a whisper of the universe's first sound. In the seething plasma of the first few 100,000 years, the cosmos was a dense, hot soup where light and matter were locked in a constant tug of war. Gravity would try to pull matter into dense clumps, while the intense pressure of radiation would push it back out. This created a rhythmic push and pull, sending powerful spherical sound waves racing through the infant universe at over half the speed of light. Then the universe cooled just enough for atoms to form, allowing light to travel freely in what we call recombination. In that instant, the music stopped. The waves froze in place, their crests imprinted as subtle overdensities in the distribution of matter. Today, we see the ghost of these waves not as sound, but as a subtle preference in the spacing of galaxies. If you could measure the distance between millions of galaxies, you would find they are slightly more likely to be separated by a specific scale, about 500 million light-years, than any other distance. This is the Baryonian acoustic oscillation, a cosmic fossil of unimaginable age. This frozen wave pattern provides cosmologists with a standard ruler of known physical size. By measuring how large this ruler appears in the sky at different cosmic epochs, we can track the expansion history of the universe with extraordinary precision. It is like finding a ruler embedded in the fabric of space itself, one that stretches as the cosmos expands, allowing us to measure the influence of dark energy across billions of years. This hidden mechanism confirms the hot Big Bang model to a stunning degree and offers one of our cleanest tests for the nature of the dark energy that drives cosmic acceleration. What other primordial rhythms are encoded in the large-scale structure of reality, waiting to be read in the light of distant quasars? A beam of light from a brilliant cosmic beacon journeys for billions of years, yet its story is written in the shadows it collects along the way. When we point our telescopes at a distant quasar, we are not just seeing the quasar itself. We are reading a cosmic barcode, a complex pattern of dark absorption lines superimposed on its brilliant spectrum. Each of these lines is a fingerprint, the signature of a cloud of neutral hydrogen gas that the quasar's light has passed through on its long voyage to Earth. This intricate web of shadows is known as the Lyman Alpha Forest, a hidden tapestry woven through the vast expanses between galaxies. The sheer number of these lines creates a dense, forest-like structure in the data, each tree representing a single cloud of primordial gas. This forest is not a static picture. It is a dynamic fossil record of the universe's youth, a timeline of how matter distributed itself when the cosmos was only a fraction of its current age. By analyzing the exact spacing and depth of these absorption lines, cosmologists can reconstruct the three-dimensional distribution of this intergalactic hydrogen. It reveals the cosmic web in its most raw and fundamental form, the wispy filaments and vast voids where the first galaxies would eventually be born. The patterns in this forest are exquisitely sensitive to the fundamental properties of the cosmos. They serve as a powerful test for the nature of dark matter. The gravitational influence of dark matter dictates how these gas clouds clump together. A model where dark matter is cold and slow-moving predicts a specific pattern of filaments, while other, more exotic possibilities would leave a different imprint on the forest's architecture. Furthermore, this labyrinth of hydrogen holds the key to understanding one of the universe's great phase transitions, the epoch of reionization. In this early era, the first stars and galaxies switched on, their intense ultraviolet radiation burning away the fog of neutral hydrogen that filled space, ionizing it and making the universe transparent to light. The Lyman Alpha Forest is the direct archaeological evidence of this process. By studying how the absorption lines thin out at different distances, corresponding to different look-back times, we can trace exactly how and when these cosmic clearing fires swept through the universe. This hidden mechanism transforms a single beam of light into a core sample of cosmic history, drilling back through time to reveal the delicate anatomy of the infant cosmos. What other primordial secrets are encoded in the shadows cast by the universe's most brilliant lights? A galaxy's majestic spiral arms are not a static sculpture, but a dynamic and potentially unstable structure. Deep within the swirling disk of stars and gas, a hidden tug-of-war dictates its ultimate shape, a balance captured by the Ostraker-Peebles criterion. This fundamental rule of galactic stability pits the ordered motion of rotation against the relentless inward pull of gravity. It calculates a simple ratio, comparing the energy of the galaxy's spin to the energy contained within its gravitational field. If rotational energy dominates, the galaxy tends to remain a stable, beautiful spiral. But if the gravitational potential energy is too high, the disk becomes unstable, buckling and twisting into a central bar. This transformation is not merely cosmetic. A galactic bar acts as a cosmic engine, funneling vast amounts of gas toward the central core. This can trigger violent bursts of star formation or even feed the supermassive black hole lurking there, igniting it into a brilliant quasar. The criterion reveals that a galaxy's fate is written in its spin and mass, a hidden dynamical mechanism that orchestrates its evolution over billions of years. Yet this balance is not maintained by the stars we see alone. The immense, invisible halo of dark matter surrounding the galaxy plays the decisive role. Its gravitational grip stabilizes the entire disk, acting as a hidden anchor that prevents the spiral structure from winding itself into a tangled mess or collapsing entirely. Without this dark matter scaffold, the beautiful, long-lived spiral galaxies we observe would be fleeting anomalies. The Ostraker-Peebles criterion is the hidden formula for galactic architecture, a simple calculation that explains the stunning diversity of forms in the night sky, linking the invisible dynamics of dark matter to the visible splendor of a spinning cosmic pinwheel. The universe's first dawn was a silent one, illuminated by no stars. For hundreds of millions of years, a pervasive fog of neutral hydrogen gas filled all of space, absorbing any trace of ultraviolet light and keeping the cosmos in a state of profound darkness. The first clue that this cosmic dark age ever existed comes from a strange void in the light of the most distant objects we can see. When astronomers analyze the spectrum of an ancient quasar, they expect to see a continuous rainbow of colors. But for quasars whose light has traveled from the deepest reaches of time, a portion of that rainbow is completely erased. A broad, dark trough cuts through the ultraviolet part of the spectrum, a gaping absence where light should be. This is the Gunn-Peterson trough, the ghostly signature of that primordial hydrogen fog. Every missing photon in that trough was absorbed by a neutral hydrogen atom on its multi-billion-year journey to our telescopes. The depth of the trough reveals the staggering density of this ancient gas. It was not merely a few wispy clouds, but an all-encompassing ocean, so thick with neutral atoms that it was completely opaque to the specific wavelength of light that hydrogen absorbs. The very existence of this trough in the most distant quasars confirms that there was a time before stars, a period when the universe was a vast, dark, and simple place. Then something changed. For quasars a little closer to us, corresponding to a slightly later era in cosmic history, the trough begins to fill in. Faint light starts to appear within the void. This is the signal of reionization, the universe's great awakening. The first generations of massive stars and quasars were switching on, flooding the cosmos with intense ultraviolet radiation. This radiation battered the hydrogen atoms, stripping away their electrons and turning the neutral fog into a transparent, ionized plasma. The Gunn-Peterson trough is our primary witness to this epic transition. By measuring exactly how the trough vanishes across different distances, we can piece together the timeline of this cosmic dawn. It was not an instantaneous flash, but a gradual process, a slow burning away of the fog as brilliant islands of light grew and merged, their ionizing bubbles eventually overlapping to clear the universe for all the light that would follow. This hidden mechanism in quasar light does more than mark a date in cosmic history. It reveals the arduous birth of structure itself. The end of the Dark Ages was the moment the universe became recognizable, setting the stage for the unfettered evolution of galaxies and the eventual rise of complexity. How long did it take for those first faint embers to set the entire cosmos ablaze with light? The faint whisper of the Big Bang's afterglow carries more than just a story of ancient temperatures. As this primordial light journeys for billions of years, it encounters the most massive structures in the universe, immense galaxy clusters filled with a superheated gas. When these ancient photons plow through this seething ocean of electrons, a subtle but profound transformation occurs. This is the Sunyaev-Zeldovich effect, a hidden scattering mechanism that imprints the signature of modern cosmic structures onto the oldest light we can see. The cosmic microwave background photons are incredibly low energy, a relic of a much cooler, denser universe, but the electrons in the intracluster medium are roiling at temperatures of millions of degrees. When a cold, primordial photon collides with one of these blisteringly hot electrons, it gets a powerful kick, like a ping-pong ball being struck by a speeding train. The photon steals a tiny amount of energy, shifting it to a higher frequency on its journey to our telescopes. The result is a specific cold shadow on the microwave sky. In the direction of a massive galaxy cluster, the cosmic microwave background appears slightly dimmer at its characteristic low frequency because those photons have been boosted away, scattering out of the line of sight. This creates a unique silhouette against the most distant backdrop imaginable. The power of this effect is its incredible independence from distance. Unlike measuring a cluster's light, which fades dramatically the farther away it is, this scattering shadow remains just as distinct for a cluster 10 billion light-years away as for one a billion light-years away. It provides a direct, clean measure of the total pressure of the hot gas in the cluster, which in turn reveals the cluster's total mass, including the vast, invisible halo of dark matter that holds the entire structure together. By combining this shadow map with other observations, cosmologists can do more than just weigh these cosmic giants. They can watch them move. The kinematic Sunyaev-Zeldovich effect detects minute shifts in the scattered light caused by the bulk motion of entire clusters flowing along the cosmic web, pulled by the gravitational tides of unseen superclusters and dark matter filaments. This allows us to trace the rivers of dark matter that define the large-scale flow of the universe itself. How many other invisible currents are sculpting the cosmos, their presence only revealed by the subtle distortions they leave on the light of creation? An invisible wind of ghostly particles flows through the cosmos, a relic from the very first second of the Big Bang. This is the cosmic neutrino background, a sea of the most elusive particles, born in the initial fire and now cooled to a temperature just a fraction of a degree above absolute zero. For every proton in the universe, there are roughly a billion of these primordial neutrinos, a whisper-thin cosmic fossil that predates even the cosmic microwave background. While the afterglow of the Big Bang paints a picture of the universe at 380,000 years old, the neutrino background carries a story from when the cosmos was barely a second old, a time of unimaginable density and heat. These ancient neutrinos have been streaming through space, almost entirely undisturbed, for nearly 14 billion years. Their sheer numbers mean they exert a subtle but significant gravitational influence on the development of cosmic structure. As the universe expanded and matter began to clump under gravity, this relentless neutrino wind acted as a drag. Their incredible speed meant they washed over the tiny density fluctuations, smoothing them out and suppressing the formation of the very smallest galaxies. We see the ghost of this effect in the large-scale distribution of galaxies today, where there are fewer dwarf galaxies than our models would predict without this neutrino damping. This is how we know they are there, even if we cannot catch them directly. Their hidden presence is etched into the cosmic web itself. Detecting these specific primordial neutrinos, however, is a monumental challenge that pushes the limits of experimental physics. They possess so little energy that they are effectively frozen, and their legendary reluctance to interact with matter makes them nearly impossible to trap. A detector the size of a planet would be needed to register just a handful of them per year. Yet, the scientific prize is immense. Measuring the cosmic neutrino background directly would open a window into physics at energies 1 trillion times higher than what our most powerful particle colliders can achieve. It would tell us precisely how many neutrino species exist and could reveal if there are other, even more exotic, lightweight particles that have so far escaped our notice. This faint, cold echo from the first moment of time holds secrets about the initial conditions of everything, a hidden current from the dawn of creation that continues to shape the cosmos in its silent, unseen flow. Beyond the singular drama of black holes, a far grander information paradox engulfs the entire cosmos. Every transformation, from the Big Bang to the endless churn of eternal inflation, must answer a fundamental question. Is information, the specific quantum identity of every particle, truly preserved? our universe began in an exquisitely low entropy state, a tightly wound spring of order and information. But where did this initial cosmic data come from? If information cannot be created or destroyed, then the starting conditions of our reality were not a true beginning, but a transformation from a prior state. This hidden informational mechanics suggests that space-time and information are two sides of the same coin, deeply woven into the fabric of quantum gravity. The very arrow of time, that relentless slide toward disorder, might be the unfolding of this initial cosmic data set, a story being read out from its compressed, ordered beginning. How is this cosmic information encoded? Perhaps, as holography suggests, the entire three-dimensional history of our universe is a projection from a two-dimensional boundary, a cosmic hard drive storing every event. Or maybe the information is preserved in the subtle quantum entanglements between different regions of space, a vast, invisible network that defines causality and connection. This ultimate mystery binds the black hole's dilemma to the universe's origin, the nature of time to the structure of space. It asks whether our cosmic story is a unique, irreversible narrative, or just one possible readout from a deeper, informational substrate that transcends the universe we perceive. Our journey through these 50 hidden mechanisms reveals a cosmos built on profound and beautiful mysteries. We have seen how particles whisper to one another across the void, how the emptiness of space holds the key to cosmic destiny, and how the very laws of physics seem fine-tuned for our existence. Each puzzle, from the stubborn stability of the proton to the ghostly wind of primordial neutrinos, is not an end point but a signpost. It points toward a deeper layer of reality, a more complete set of rules waiting to be uncovered. These enigmas remind us that our universe is far stranger and more wonderful than our everyday experience suggests, a grand cosmic story still being written. As cosmologists piece together these clues, from the event horizons of black holes to the faint echoes of the Big Bang, we edge ever closer to a vision that could unite the very large with the very small into a single, elegant theory of everything. This quest reshapes not only our understanding of the cosmos, but our place within it. We invite you to reflect on these ideas and share your thoughts. Which of these hidden mechanisms captivates your imagination the most? Let the conversation continue below. If these cosmic secrets have sparked your curiosity, subscribe for more deep dives into the wonders of the universe. Keep looking up and questioning, for the cosmos holds countless more secrets, each one a doorway to a reality grander than we have yet dared to